Hello and welcome to the feedback video for assignment 2 motion. In this video we're going to be looking at the first few questions of the assignment, and at the end of the video you'll be asked to complete a question that includes some similar concepts. Please pause the video, attempt the question and hand it back to your teacher as soon as possible. Okay, so if we look at the first question, it's wanting you to describe the motion of a hockey player during a match, and it gives you her distance time data. Now, using a distance time graph, we can work out our hockey player's speed, and that's important when discussing and describing her motion. From mathematics and in your physics class, you should be aware that you can calculate the gradient or the steepness of this graph by doing the change in the y-axis or the rise divided by the change in x-axis or the run. And if you look at this graph, because we've plotted distance on the y-axis and time on the x-axis, we're actually doing the change in distance divided by the time taken, and this is our equation for speed, hence why the gradient of the graph is the same as the speed. So if we first look at section A, you can see that the graph is a constant straight line. It has a constant gradient, it does not change, and therefore we can say that the hockey player has a constant speed. The 4 meters per second I've just taken from doing the 20 meters, which is the distance covered, divided by the 5 seconds taken. For part B, the next 10 seconds, the gradient here gets less and less and eventually is a flat line. Well, a flat line on a distance time graph is where our hockey player will have a speed of 0, so they'll be stationary, and where the gradient decreases, our hockey player's speed must be decreasing, and we call that deceleration. So they're decelerating to a stop. And finally, section C, just like in section A, is a straight line. There's no change in gradient and therefore no change in speed, unless we can say is a constant speed. There's 7 meters per second. If we look at the graph, is a change in distance of 70 meters divided by the time taken of 10 seconds, and therefore we get 7 meters per second. So you can see it's a steeper gradient, it's a bigger speed than in section A. Now, our next question wants us to explain the difference between 3 key terms when discussing motion. So we're going to look at speed first. If you watch our little man as he runs across the screen, you can see there I've monitored his distance and his time, as they're 2 key variables when discussing speed. And our definition of speed, which at level 2 we're giving is the rate of change of distance travelled by an object. And if you look at his motion across the screen, you can see this is a constant speed because the rate at which he changes his distance is constant. Each second he is changing his distance travelled by 5 meters. Next we look at velocity, but before I talk about velocity we need to understand the term displacement as we define velocity in terms of displacement. Displacement is defined as a measurement of distance from a specific point, and therefore it needs a direction and is a vector quantity. When dealing with vector quantities, we need to give not just a size or magnitude, but also a direction. Now, this direction can be inferred from either a positive or negative, if we have on our diagram a positive direction and a negative direction, or right and left. In this case, I'm going to use positive for being towards the right and negative towards the left. So if we look at our man and his starting position, if he was to walk 10 meters to his right, we'd say that the distance he's travelled is 10 meters, and his displacement is 10 meters to the right, or a positive 10 meters. If he continued this journey in a straight line, but went back towards his start position and past it, then his total distance at the end of this journey, that can be seen from the diagram, would be the 10 meters he walked to the right, and then the 15 meters he walked to the left. So it would be 25 meters. However, his displacement would only be 5 meters to the left, or negative 5 meters. Okay, so now we've got a grasp of displacement, we can now look at velocity. So velocity is defined as the rate of change of displacement. In this top diagram, our runner is running from left to right, they're running in the positive direction, and their displacement each second is a positive 5 meters, and therefore their velocity is 5 meters per second. In the bottom diagram, our runner is running from right to left. They're running in the negative direction. So their displacement each second is minus 5 meters, and therefore their velocity is minus 5 meters per second. So the last term to look at is acceleration, and here we define acceleration as the rate of change of velocity of an object. Now, because velocity relied on displacement, and displacement was a vector quantity, that means that velocity is a vector quantity and also acceleration is a vector quantity. That means they must have size and direction. So here again we're looking at left being negative and right being positive. And in our first diagram, our top diagram, we're going to look at a runner as they change or they increase their velocity as they run from left to right. They're running in the positive direction. You can see that even though their distance might not be constant like it was for velocity each second, the change in their velocity, which is marked underneath, is an increase in 3 meters per second. And this change is constant each second. Now we can also get a deceleration. Again, I'm going to talk about it in terms of a constant deceleration. We'll take the same magnitude, so 3 meters per second squared, but this time in the opposite direction. So here our runner is slowing down, and you can see that although again his change in distance is not constant, the change in velocity is constant. So he started at 9 meters per second, and each second he decreased his velocity by 3 meters per second. Now that's not to say that a positive value for acceleration is always an increase in velocity and that a negative value is always a decrease. It is dependent upon the direction. Okay, so that brings us on to the last question in this video, and it wants us to calculate the distance travelled by a hockey player who accelerates uniformly at 1.8 meters per second from a standing start, and it wants to know the distance after 2.5 seconds. So I've drawn a diagram with this just to help show what this question is asking, and we can use a kinematic equation because it tells us that the acceleration is uniform. It doesn't change, it's constant. The first thing that you want to write down with this question is the variables that you're given. So here I've highlighted them and I've written them down. It tells us that the player began at a standing start. That's our initial velocity of 0 meters per second. It tells us that she accelerates uniformly at 1.8 meters per second. It tells us that the time that she's running for is 2.5, and it wants me to calculate how far she's ran, so therefore her displacement from where she began to where she is after 2.5 seconds. The next step is to choose the correct kinematic equation. In this case it would be this one here, where it has all 4 variables, the 3 known and the 1 unknown. So the last step, once identifying your equation, is just to substitute in the values. Be careful when you do this. I tend to bracket it when I put it into my calculator, as it just keeps it clean and it reduces the risk of any error. And once you put those numbers through, you should get an answer for displacement of 5.625 meters. Now if you look in the question, the 2 values that we were given to 2 significant figures, and we can only be as accurate as our least accurate piece of data, and therefore our answer should be to 2 significant figures. So my final answer for displacement, or how far she's ran after 2.5 seconds, is just 5.6 meters. Right, if you could pause the video, complete the question shown, and hand it back to your teacher as soon as possible.